Welcome students. In the previous lecture, we have discussed about the term electric flux. Today's topic is Gauss's law. The learning objectives of the topic are: after the completion of the topic, students will be able to state Gauss's law and also deduce the expression for it. Also, you will be able to derive Coulomb's law by using Gauss's law. Now, first of all, what is Gauss's law? In the previous lecture, you all have read about electric flux. What was electric flux? That is the passage of electric field lines through a given surface. Now, this Gauss's law, it is a relation between electric flux and the charge enclosed inside the surface. So, Gauss's law relates the net electric flux through a closed surface to the total amount of charge present within the surface. So, net electric flux is equal to 1 upon epsilon naught times the electric charge inside the Gaussian surface. So, mathematically, phi is equal to Q by epsilon naught, and phi is electric flux. You all have studied this in the previous lecture. That is given by the whole integral of E dot dA, which is equal to Q upon epsilon naught, where Q is charge enclosed and epsilon naught is permittivity of free space, whose value is equal to 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. Now, mathematically, Gauss's law can be expressed as phi is equal to 1 upon epsilon naught times the charge enclosed within the given surface. Now, what is phi? That is electric flux. Q is charge here, and epsilon naught is permittivity of free space. Now, Gauss's theorem can be stated as the surface integral of the electric field intensity over any closed hypothetical surface, that is Gaussian surface, in free space is equal to 1 upon epsilon naught times the net charge enclosed within the surface. So mathematically, simply, it can be written as phi is equal to E dot ds, the whole integration, which is further equal to 1 upon epsilon naught times the total charge enclosed in the surface. Now, let's do the mathematical proof for Gauss's law, and that is for spherically symmetrical surface. Now here, what we have to do? We have to consider an isolated positive charge inside the center. That is, consider a positive charge at O. Now we have to consider a hypothetical Gaussian surface, and that hypothetical Gaussian surface here will be a sphere whose radius is r. Now the electric field intensity will be normally outward because it is plus q charge. Therefore, electric field intensity will be radially outwards. And we have shown here one electric field intensity, that is E vector. And we are considering here this small surface ds. Now, applying Gauss's law, d phi, which is equal to E dot ds, is further equal to, the value of E is 1 upon 4 pi epsilon naught q upon r square, r unit vector, which is the direction radially outward, and ds vector will be equal to ds n unit vector. Its direction is also perpendicularly outward. Since E vector and ds vector, they are in the same direction, therefore the angle will be cos 0, which will be equal to 1, and simply d phi can be written as 1 upon 4 pi epsilon naught q ds upon r square. Now this flux is through this small surface, and we have to find the electric flux through the whole given surface. So phi will be equal to integrating d phi, which substituting the values, that is 1 upon 4 pi epsilon naught q upon r square will be taken outward and the integration will be at ds. So, small surface is ds, integrating the whole surface, that is the surface area of this will be equal to 4 pi r square. Cancelling the terms, we will get q upon epsilon naught. So, this is the mathematical formula for Gauss's law, that is phi is equal to q upon epsilon naught. Now, let's come to the next, that is deduction of Coulomb's law from Gauss's law. Now here Gauss's law is given to us and we have to deduce Coulomb's law. Again, what we have to consider? We have to consider an isolated positive charge at O, and then we have to consider a Gaussian surface, which is a hypothetical Gaussian surface, and that will again be a sphere of radius r. Now again, the electric field of plus q will be radially outward, and since ds is also perpendicularly outward, therefore phi will be equal to E dot ds, which is equal to q upon epsilon naught. This is Gauss's law. Since E and ds are in the same direction as we have done in the previous case, that will be cos 0 and which will be 1. Now again using the Gauss's law, and now taking the electric field outside because it is constant over here and integrating over ds. Now for small surface we are having ds, and for full surface we will integrate it and it will be this, and the surface area for this will be 4 pi r square. So E into 4 pi r square, which will be equal to q upon epsilon naught, and from here we will get the value of E, that is q upon 4 pi epsilon naught r square. Now consider a test charge or q naught simply, which is placed at a certain point where electric field is to be determined, and then force will be given by q naught 4 pi epsilon naught r square, which is Coulomb's law. Hence what we have done here in this article, we have deduced the expression of Coulomb's law while using Gauss's law. And in the next articles we are going to study the application of Gauss's law. Till then, stay happy and stay blessed.